Okay, so second second chapter on entropy. Well, at least the only chapter here in second semester. And this picture here to the top, it shows the heat tax, and on the right says free energy, and the bottom says perpetual motion. And the idea this thing would roll something, and the water would flow uphill back to the heat tax. And so perpetual motion, the idea of this perpetual motion will never happen because you can't break even. You can't break even because of entropy. Entropy is just order. So let me explain this in terms how we generate electricity. Typically speaking, most electricity is made via a turbine. You have a heat source, typically burning coal in the United States. You can also have nuclear power. We get about 20% of our energy from nuclear power, almost half of it from coal. But you heat up something, energy source, creates steam, and the steam turns a turbine. Then you condense the water back and it recycles through there. And you have a generator. A generator is basically a bunch of magnets that spin around a wire, and that induces current flow in the wire. And then the electricity is carried over high power lines to your home, and then it turns on the electrical coil there for your stove. So, how much energy is going, like, so when you boil water on your stove top using electricity, what's the efficiency of that energy getting to you? Well, when you have the flame, you find the flame, is all the energy from the flame going to the water to turn into steam? And the answer is no, it's not. Also, it's heating up the sides of the container. And then is all the energy from the turbine going to the generator? No, there's friction loss going on there. And the energy in the high tension wires. Is all the electricity, is it conserved? Are we losing electricity? Yes, you are. You are losing electricity as it goes from the power plant to your house. And then is all the heat going from the heater in your house to whatever it is you're cooking? And the answer is no, you're losing it to various things, like just radiates out or heats up other things. So all of that is because of entropy. So this order. It's unfortunate that we waste all that energy, but there's not a whole lot we can do about this because that is one of the natures of the way of the universe. Uh, and it brings us to alternative energy. This is a load profile for Honolulu, or for the island of Oahu, and I have written here in blue. This is typically what most of the electricity works for around the country. That you have a peak around 7 8 a.m. and it stays high till about 3:34, and then it lulls till about 9, and then it goes to the baseline. Here in Hawaii is weird because our peak is actually between the hours of 6 to 9 p.m. That is where the largest load is on the grid, and that is because people come home and then they're working and they come home and they do things like television. They cook things in the kitchen and run appliances like the laundry. On the mainland, well, the rise is different here in Hawaii versus the mainland because we don't have a lot of industry in Hawaii, and the industry is what consumes electricity mostly in the mainland. And we have quite a bit of solar. So if you see solar, and if you can, it's actually best if you were to run your appliances and do your cooking in the middle of the day because we have that solar energy that are not necessarily using. So uh, that's the if you can. I mean, I know that people's schedules are different, but middle of the day is really the best time to do things here in Hawaii. At least if you're somewhere else, it could be something different. Maybe in the middle of the night if you're if you can. So here's another thing with wind farms. So this is 2008. So this is the estimated power generation to wind farms. So that's one thing with alternative energies. Like, oh, it's so easy. Here's the capacity of 2,800 megawatts. So you can see you have that capacity there, but the actual energy output of the wind farms. This is two wind farms joined together. So you can see the wind farm energy is really not that usable, and you get areas where it goes down to zero. So this is really hard for electrical grid. So wind energy, like I said, is not very useful at all. And this is a typical profile for no wind. So I mentioned the highs and lows, and these data are from Canada. So the there's high usage there in the middle of the day because of heaters in the winter time, and then not so much in the summer. I mean, Canada's pretty far north, so you don't have to have as much electricity in the summertime like we do in Hawaii for the AC. And if you see some of these things, here's high wind, medium wind, and high wind. You can see high wind is actually the worst case scenario. Well, I guess the worst case scenario is no wind, but high wind is not very useful for wind farms. I mean, the best thing for wind farm is slow and steady wind. And as we know here in Hawaii, when in the summertime when the trade winds die down, that's when everyone turns on his or her AC unit, and that's also when we get the least amount of energy from the wind. So we have an issue there with this, and the wind energy is just not very useful. So why is that? Well, because it's not consistent. It's not consistent. So then what do you do with this energy? I mean, you're putting spikes and valleys into your electrical grid, and what is that going to do? So it's questionable how much fuel we actually save by using wind energy. So that's Canada. Here's South Point here in Hawaii Big Island, a very windy place. You can see you still have the surges and the valleys. It's fairly consistent, not as consistent. And this is on Oahu. So we fit that there. So my point though there is that it has to do with entropy, and entropy is part of our discussion of thermodynamics. And let's talk about the limits of thermodynamics. You can tell what the end products are, but not how quickly it'll react. So we know, for instance, if you take a diamond out from beneath the earth and at this temperature and pressure, diamonds are thermodynamically unstable. They will turn back into graphite, but they will take a very long time. And I mean, I know there's some rings, so like wedding rings frequently will mix platinum and gold together. Well, the platinum will cause the gold to corrode, but how long is that going to take? Like hundreds or thousands of years. So, I mean, we can show that it will happen, but we don't really know how fast it's going to go, or it could be a very long time. That's the limit of thermodynamics. So even if there is something that is high and very unstable, doesn't mean the chemical reaction is going to happen very quickly. We also have the processes that are spontaneous and non-spontaneous. So things work the same way with people, right? So if you have a spontaneous person, the person's always like, all right, look at that, there's a waterfall, I'm going to go jump in the waterfall. Oh, look at this, I'm going to go climb that. I'm going to go, let's go out, let's go do these things. Like, that's a spontaneous person, right? A spontaneous person always doing random things. Can you get a non-spontaneous person to do something? Like, yes, you can. You have to cajole the person really hard to do it, though. You have to promise things. You have to give them money or something like that. And the same thing is true for chemical processes. So spontaneously, iron rust. If you sit iron there, it'll do nothing. It's going to rust. Can you turn rust back into iron? Yes, you can. How do you do it? Well, if you apply heat and you put carbon in it, so reduction with carbon, that'll do it. So energy and something to reduce it. Energy and electrons will cause rust to turn back into iron. So it can happen. Also, some endothermic processes do happen, like ice melting. Ice melts, right? But that absorbs energy. So why does this happen? Why are we having endothermic processes happen? And it's because of entropy. Entropy is disorder. And entropy is the number of ways to achieve a particular state. So the more numbers of states, the higher probability of state, the more likely that's going to be in. And things will move towards the higher likelihood of states. So this is two definitions of entropy. Entropy is defined, I mentioned this before, as the Boltzmann constant times the natural log of the number of states. Entropy is also the reversible heat transfer divided by the temperature. So it tells you another thing. So two things that these equations tell us. So the first equation, if there's one state, that means entropy is zero. So the natural log of 1 is 0. So that's the third law of thermodynamics, is the definition of entropy there. And then if entropy is reversible heat transfer over temperature, if there's no heat transfer, there's no change in disorder. So if you want something to not become more ordered, what do? You prevent heat transfer. So insulation. So if there's insulation, a process will have no change, no change. So term adiabatic. Adiabatic means no heat transfer. Adiabatic also means isentropic. Iso entropy, same entropy, isentropic. Adiabatic and isentropic are interchangeable in that regards. So what do I mean by the number of states? So let's look at so just 4 particles. So if we have 4 particles and then we open up a valve, and where do we find those gas particles? So the likelihood of having just having 4 particles in one container and not this is 2 out of a certain number that could happen, and you look at compare to it versus them being evenly split. The number of possible states for this is 6. So the one on the right, this microstate here, this is much more likely. This is where the entropy is higher. S is higher than here. Here entropy is low. So and it's kind of like, okay, so this is 4 particles. So what if you have something huge, like say a mole of something, right? 10 to the 23rd. It's much more likely when you have the large number of states that it's just evenly split. I'll give you so let's see here. I walked into a room. I'm right now. I'm recording this video in a small room. When I walked in the room, was I thinking, oh gee, is all the gas going to be in the corner of the room, and I'm going to walk into a vacuum? Is that possible? Yes, that's possible. Is it likely to happen? No, it's extremely unlikely. Just like it is here to have 4 gas particles in one container and a vacuum in the other. This is fairly unlikely. But I mean, this is just with 4 particles. What if you have a huge amount? Let me give you a medium example. I think I used this before, but Skittles. I like Skittles. What if you took a bag of Skittles and you arranged them by color and you put them into a jar? What happens if you shake the jar? Is it going to line up all nice and even, or is it going to be randomized? Like, well, it's going to be randomized, probably. Is it possible for everything to line up properly and perfectly? The answer is yes, it is possible. Is it likely to happen? No. It is very unlikely for that to happen. You'll be shaking that jar for a long time before they all even out. So let's look at this. Which of these following has a change of positive entropy? Or so which is a change of positive entropy? So in number A here, we have concentrated in one container, and so 4 in one container, 2 in the other, and then it goes to evenly split for all out. So which one has more states? Which one's more likely? This one is true. This one has more states. The top one is definitely a positive delta S. So B, you go from very evenly split to concentrated. And because of this, the delta S is going down. So this is more ordered. So remember, entropy is disorder. So this is ordered here, and it goes towards more disorder. Here goes from disordered to ordered. So going in that direction does not typically happen randomly. And here, this is disordered here and ordered here. Then the middle one stays the same. Because of this, the entropy change is going down as well. So the one here that has a positive delta S is A. And with everything with thermo, if you remember from previous semesters, the defining the system and the surrounding is a large part of your battle. So you pick your system, and then picking your system, then you try to make the math work out to make the system the easiest to work with. And everything that's not in the system is in the surroundings. And also for change is always final minus initial, and the entropy of the universe is the entropy change. So entropy change of the universe is the system plus the surroundings. And the second law of thermo is the entropy of the universe is greater than or equal to 0, which means it's always increasing. Also remember, entropy is defined, one of the definitions is heat transfer of temperature. So if there's no heat transfer, there's no entropy change. And also, well, we're going to include another equation here. The entropy change of the surroundings is minus the enthalpy change for the system divided by temperature. Another thing with entropy changes is moles of gas. So if you have 2 moles of gas going to 1 mole of gas, so 2 moles of gas is more disordered than 1 mole of gas, entropy goes down. So, and then here you have no gas on the left and 1 mole of gas on the right. So if the moles of gas increase over the chemical reaction or physical process, then I guess there wouldn't be a physical process here. This would be a chemical reaction. Physical process would be like water boiling. So increasing the moles of gas means a positive increase in entropy. So let's do this for an example. Calculate the entropy change for this reaction here. So you have propane plus 5 oxygens makes 3 carbon dioxides and 4 waters. So let's do this. Okay, I was looking for that. In the delta H reaction is minus 2044. Calculate the entropy change to the surroundings associated with this at 25 degrees Celsius. So the entropy is equal to minus delta H reaction all over the temperature. So this is minus 2044, and it's in joules. 1,000 joules divided by 298. Oh, it's in a minus. So minus 2,044,000 joules, or 2,044 kilojoules, all over 298 Kelvin. And the answer then is, I always write out, like I said, I write out the answer in joules whenever I see kilojoules, because then I forget about it when I put it in a calculator. And then it's going to be 6,860 joules per Kelvin. So entropy change is positive. Determine the sign of the entropy change for the system. So because we're going from 6 moles of gas to 7 moles of gas, delta S for the system is the positive change, because we're going towards more disorder. And then determine the sign entropy change for the universe. Here in this case, delta S universe. It's the system plus the surroundings. So it's a positive number plus a positive number, and adding two positive numbers will always be a positive number, right? So by A, we determined that the entropy change for the surroundings is positive 660 or 6,860 joules per Kelvin. And the entropy change for the system is positive, so those are two positive numbers. We are definitely getting an increase in change of entropy for the universe. Will this reaction be spontaneous? The answer is yes. This will be a spontaneous reaction. Does that mean it's going to happen relatively quickly? And the answer is no. So propane burning at 298 Kelvin, that's 25 degrees Celsius. That is, it happens very slowly. So remember that. It's a limit of thermo. It can tell you if it's going to happen, but it can't tell you how fast. And this is not going to happen fast at this temperature. Okay, so you can give this a try. Try this then for this chemical reaction here, like so. And we're done for the first section.